Hello. In this new module on derivatives, we'll revisit finding maximum and minimum values of a function. We'll also cover critical values and computing extrema. Prerequisites include familiarity with basic derivatives of elementary functions and fundamental mathematical operations. Let's begin with the definition of maximum and minimum. Consider a function f defined on an interval I and containing the point c. We declare that f of c represents the minimum of the function within the interval I if the value of the function at c is the smallest among all the values that f can take for different x values within the interval. We declare that f of c represents the maximum of f within the interval I if the value of f at c is the largest among all the values of f for various x within the interval. While this definition may seem a bit abstract, graphically, we all have an intuitive understanding of what maximum and minimum mean. Important notes. The terms maximum and minimum of a function are occasionally referred to as extreme values or extrema of a function. You might come across exercises that ask you to calculate the extrema of a function, which essentially means finding the maximum and minimum values. Additionally, they are sometimes labeled as absolute or relative maxima and minima based on the context. Key theorem. The extreme value theorem states that if a function is continuous on a closed interval from a to b, then the function f reaches either a maximum or minimum value within that interval. Keep in mind that a function is considered continuous when it can be graphically represented without the pen leaving the paper. A note, what this theorem gives us is the existence of the maximum and that minimum. It guarantees the existence of that maximum and minimum, but does not tell us how to calculate it or where it is. Let's see a little bit what this consists of graphically. This way we review what is maximum and minimum. Consider this function, which is defined for the interval from -1 to 2, with both values included. Is this function continuous? Certainly it is continuous. You can depict it without lifting the pen from the paper. Furthermore, it's a segment of a parabola, making it a polynomial without any issues in terms of continuity. Where does this function have a minimum? The function reaches its minimum at 0. You can deduce this from the graph. There's no value of the function that is smaller than 0 in this interval, making it the absolute minimum. Additionally, look at the point 2. It appears to be around 6, if I'm not mistaken. At 2, the function reaches an absolute maximum. The value of the function at this endpoint is the largest of all the values of the function. This clearly works. And the theorem holds because we have required the function to be continuous. If the function were not continuous, the theorem might not be applicable. A definition. If there exists an open interval that includes a point c, and within that interval the function f at that value c is at its maximum, we refer to f of c as a relative maximum of f. Also, if there exists an open interval that includes c, and within that interval f of c is at its minimum, we label f of c as a relative minimum of f. How does this definition differ from the previous one? Consider this scenario. Imagine that this function, which represents a cubic function, is not defined between -1 and 3. It's defined from negative infinity to positive infinity. This means that the function drops to negative infinity on one side and rises to positive infinity on the other. Within this range, we have two peculiar points that are going to be the maxima and minima. So, what does it mean when there is an interval in which the function is at a maximum? Let's examine a small segment, say, from -0.5 to 0.5. If we concentrate on just this portion of the function, we can deduce that the value at f of 0 is the maximum within that interval. However, we can't guarantee it's the overall maximum for the entire function because, as you can see, it goes up beyond that point. Thus, we don't call it an absolute maximum. We refer to it as a relative maximum because it's the largest value within a specific environment. The same logic applies to the relative minimum. For instance, consider 2. Within this small segment, if we focus only on this local portion of the function, the value at 2 is a relative minimum. A more detailed definition. Let's delve into this further. Consider a function f defined at a specific value c. If the derivative at c equals 0, or if f is non-differentiable at c, we designate c as a critical value or critical point. It's crucial to recognize that a point can be a critical value or critical point under either of these two conditions, when the derivative at c equals 0, or when the function f is non-differentiable at c. What does this tell us? What exactly is a critical point? Recall that if we have a function of this form, we've previously defined what the tangent line is. The tangent line, for instance, at this point would appear something like this, going from top to bottom. Similarly, you should already know what the tangent line would look like at this point, at this relative maximum. Have you considered what the tangent line would be like? We have already examined it in some instances in previous classes, and it would essentially be a horizontal line. What does this indicate? It basically means that the slope of that line is equal to 0. Furthermore, you are aware that the slope of the tangent line is equivalent to the derivative of the function. In other words, it appears that at maximum and minimum points, the tangent line has a slope of 0, and consequently, it is going to be classified as a critical point. This provides you with a hint regarding how to calculate the maxima and minima. However, you must be careful because critical points or critical values also include those points at which the function is not differentiable. So you need to pay close attention to that aspect. Here's a theorem. If f has a relative maximum or minimum at x equal to c, then c is a critical value. We have seen that with the graph a little while ago. If there's a maximum or relative minimum, which implies that the function is continuous at that point and is also differentiable, you'll observe that the tangent line is horizontal. Consequently, the derivative at that point is 0, aligning with the definition of a critical value. However, we must also consider situations where the function may not be differentiable at a particular point. But what's crucial is that if f has a relative maximum or minimum at a point c, then c is a critical value. Nonetheless, we'll see later that the converse may not always hold true. So what will be our strategy for identifying the maxima or minima of a function? To discover the relative extreme of a function within a closed interval from a to b, we'll stick to the following steps. First, we'll determine the critical values of the function f at a and b. How do we calculate them? Pay attention, I covered it earlier. We'll differentiate the function, set the derivative equal to 0, solve for the points that nullify the derivative, and also identify those points where the function is non-differentiable. These constitute the critical points. Secondly, we'll assess the original function, not its derivative, at every critical value acquired in the first step. Additionally, we'll ensure that these values lie within the open interval a to b. In other words, if the critical point is 400 and our interval was from 1 to 2, that value won't be considered. We focus solely on the critical points or critical values that fall within the open interval. The third step involves evaluating the function at the boundaries of the interval, which includes the critical values that fall within and the endpoints of the interval. So, how do we determine the maximum and minimum? It's quite simple. After evaluating all the function values, including the critical values and endpoints, the largest among them represents the maximum, while the smallest denotes the minimum. The process is straightforward. Let's go through an example. Consider a polynomial function, 3x to the power of 4 minus 4x cubed, within the interval from minus 1 to 2. In the first step, we differentiate the function to attempt calculating the critical values using the traditional method, which entails setting the derivative equal to 0. The differentiation process is quite straightforward for a polynomial. We'll bring down the 4, resulting in 12x cubed, and for the second term, we'll multiply minus 3 by 4 to get minus 12x squared. We then set this derivative equal to 0. To simplify, I've factored out any common factors where possible. For example, I've factored out the common factor of 12 and x squared. What remains is x from the first term, and in the second term, there's a constant 1 left, which was multiplying everything. A product of two elements that equals 0, that occurs when either the first element is 0 or the second element is 0. So, I have x equals 0 and x equals 1, where x equals 0 cancels out the first term, and x equals 1 cancels out the second term in the derivative. Therefore, we have two critical values. Now let's proceed to examine the critical values and extrema in the function. I've set up a table where I've listed the points, 0 and 1, which are the critical values obtained from the derivative, and I've indicated the extrema. However, let's go back for a moment. The derivative of a polynomial is once again differentiable and continuous, nearly perfect. There are no points where the function is not differentiable, so there's no need to introduce additional points. It's crucial to remember that critical values include not only those where the derivative equals 0, but also those points where the function is not differentiable. In the case of a polynomial, the function is differentiable at all points, so no additional points need to be considered. Returning to the table, I've listed the critical points obtained from the derivative and included the interval's endpoints. What's the next step? We evaluate the original function at each of these points. The function yields a value of 7 at minus 1, 0 at 0, minus 1 at 1, and 16 at 2. To determine the maximum and minimum, just take a look at the values on the screen. Among these values, 16 is the highest, meaning it is the maximum, while minus 1 is the lowest. indicating the minimum. Therefore, the function reaches a maximum at the point 2, 16, and a minimum at the point 1, minus 1. A note, at the critical value x equals 0, there is neither a maximum nor a minimum. This means that the reverse of the theorem is false. The theorem stated that if there is a maximum or a minimum, then it's a critical value. However, a critical value, like 0, is critical because the derivative at 0 is 0. This can be easily demonstrated. It is neither a maximum nor a minimum. It's a peculiar point that we'll explore later on. It's an inflection point. What's crucial to remember is that not all critical values represent maximum or minimum points. This is not always the case. This analysis must be performed systematically. How can this be? Graphically, it's quite evident. In this graphical representation at 0, as you can observe, there is neither a maximum nor a minimum. It's a transitional point between concave and convex sections. However, we'll delve into this further and give it another name. And as you can see, in minus 1 it reaches the minimum, and in 2 it reaches the maximum. Let's look at another example that's a bit more complex. In this case, we're examining the function 2x minus 3 times the cube root of x on the interval from minus 1 to 3. Why is it a bit more complex? Because of the fractional exponent. How do we approach this process? Exactly the same way. The first step is to differentiate the function. How do you differentiate this? It's straightforward. 2x becomes 2, and 3x raised to 2/3 becomes 3 times 2/3, times x raised to 2/3 minus 1. Simplify. The 3 goes with the 3, leaving me with 2 minus 2, x to the power of 2/3 minus 1, which is minus 1/3. Let's adjust that a bit. That simplifies to 2 times 1 minus 1, divided by x to the power of 1/3. I'll write it this way for clarity. That's the first derivative. It might look a bit complex, but let's see what happens when we set it equal to 0. When we set it to 0, a fraction is 0 when its numerator is 0. In this case, I've simply moved the 2, which is multiplying to the other side by dividing, making it disappear, and I'm left with this. This fraction equals 0 when the numerator equals 0. Now, if the numerator equals 0, it implies that x raised to the power of 1/3 is equal to 1, and thus x equals the cube root of 1. Note that there are two complex solutions to this equation, but for now, we're focusing on real solutions, which means we have a critical value of x equals 1. Now, you need to be cautious. Is this the only critical value? Well, let's consider the function. Is this function defined for all values? The answer should be no. If x is 0, you would be dividing by 0, which poses a major problem. The function is not differentiable at 0. Therefore, 0 is also a critical value. I have added it to the list because it is a critical point due to the derivative not being defined at 0, as we are dividing by 0. Taking into account the extremes of the interval and the critical values that we have obtained, which are 1 and 0, we obtain the following. Notice. Here, I've listed the points 0 and 1, along with the two interval extremes, and calculated the function's values at these points. The function at minus 1 is worth minus 5, at 0 it's 0, at 1 it's minus 1, and at 3 it's minus 0.24. What is the maximum and what is the minimum? In this case, the smallest value is minus 5, and the largest value is 0. So the minimum occurs at minus 1, minus 5, and the maximum occurs at 0, 0. The graph of the function is shown here. It's defined only between minus 1 and 3, and it reaches a minimum at minus 1, minus 5, and a maximum at 0, 0. What have we seen? We introduced the concept of maximum and minimum, critical values in a function, and reviewed the calculation of extrema for functions. I hope this has been helpful. Thank you.